Thank you, Jason. Hey, everybody. Can you all hear me, I guess? Monitoring serverless things, yeah. It's my guy, Seth Fargo, actually submitted this talk initially, so I've had to kind of build on top of it. And we kept the title the same. It's pretty much the same talk, but a little bit different with my own spin on it. So basically, I'm Mandy Waite. I'm the TLM for Cloud Infrastructure and Ops Advocacy at Google, Developer Relations. So I run the team for infrastructure and operations, which is kind of weird for DevRel. It's kind of new. It's a new territory for us, but we've got an ever-growing team, and we're working with people like you to help solve your problems in the cloud. The picture of Hermione Granger is because of the weather and my hair, which is normally quite straight, but now it's just kind of ballooned because of the weather. So that's not really me. That is Hermione Granger from Harry Potter. That's me. So we're going to talk about serverless things, and the first thing I want to do is talk about serverless because I find it fascinating how many definitions there are about serverless in the world. So I'm going to give you my own spin on it. There is no real canonical meaning for serverless. It means a lot of different things to a lot of different people, but to me and where I'm coming from, it means this. Back in the old days, we used to have mainframes, and then we swapped our mainframes for physical servers we could ship into our offices and into our server rooms and into our data centers. And the world was good because we had lots of compute power at our disposal. We virtualized everything ultimately as well. Virtualization empowered us to do lots of different things, carve up hardware into small proprietary slices that could be dedicated to specific applications. And that also saw the advent of the cloud and became the public cloud, but back in those days it was just a cloud. And what we could do with that is we could provision all of those things that we had before, memory, CPU, virtual machines, NICs, all of that stuff. We could do it in the cloud on demand. Very, very powerful model whereby we can get at very, very quickly large numbers of servers that can run our workloads for us. And people saw the power in that, and they actually added cloud to their own infrastructure, to their own data centers, to their own on-premise installations, and provided that same model to their people so that they could provision stuff on demand, but using their own infrastructure rather than using the cloud. They didn't think the cloud was safe. And then something kind of magical happened. Google had this scale problem a long time ago. And I'm not going to attribute all of this to Google. Absolutely not. This talk isn't about Google. But something magical happened at Google whereby we faced a massive scale problem. We had to scale very quickly, very rapidly to very large volumes that we couldn't handle before. We had lots of machines, but providing those machines and giving them access to it, giving our software engineers access to them was very difficult. So we came up with a new way of doing things. We'd just take a whole bunch of machines, say 5,000, 10,000 of them, bunch them all together and call them a cluster. And then we would just allow people just to throw work onto that cluster and have it run. They didn't have to care about the machines that it ran on, it just ran. A very, very powerful model that we kind of leveraged to do other things as well. We built internal services like Prometheus, which was App Engine, ultimately, and also Dremel, which was BigQuery. Very much built on the same principle, is that you do not have to provision anything to make your application run and to have it scale automatically. Dremel came about because we needed to analyze very, very large logs, terabytes of log data, very, very quickly, seconds rather than minutes or hours. We needed to spin up workloads internally, platform as a service. And App Engine effectively allowed us just to write some code and to throw it at App Engine and let it run for us. We made those things available publicly. And then sometime afterwards, Kubernetes comes along. And Kubernetes takes our model that we've developed internally and exposes it to the rest of the world. So now you can actually take all of your fleet of machines and expose them as a cluster to your people who can just say, schedule this work for me, and it will be scheduled for them. The next step was, there's many more of those services as well. Everything is going in this direction. AWS Lambda came along, Google Cloud Functions, Knative, which was announced recently at Google Cloud Next. All of these things offer kind of functions as a service, the ability to run work in the cloud based on events. So we attach we create some code, and then we have some kind of event fire off and execute that code, and we can do that at scale. And that's another very, very powerful model. But there's no infrastructure involved. There's no need to set up software stacks or anything like that. What we can do is take what we have and what we care about and turn it immediately into business value. And I think about that currently, and I'm still thinking about this quite a lot, that could be data, and it could also be business logic. business logic, the kind of things you need to do in order to get your workloads done, and data, the kind of work, the kind of stuff you need to get analyzed or manipulated in some meaningful way. And data could mean things like a large corpus of images that you're going to push into some kind of machine learning algorithm. But it could also mean log files. It could also be data where you monitor people's interactions with your application or your service. So all of these things are effectively serverless. They don't have servers. They have no infrastructure behind them. There are physical machines. I think with Kubernetes, ultimately, we'll end up with losing the notion of a machine entirely, nodeless, potentially. We may even in our data centers be able to scale vertically, add memory on demand to have very, very large machines effectively. But we can just do away with the idea of machines. We can just say, I want CPU. I want X amount of CPU. I want 1,000 CPUs. I want 1 petabyte of RAM to run a workload. And we'll be able to provision that because we can scale vertically. All those kind of things are going to be happening in the future, and the machines will go away. And ultimately, we end up in this kind of nirvana of a modern-day cloud, the next wave of cloud, the Mode 2 cloud, as Gartner would probably call it, where everything is like that. We forget about virtual machines. We forget about virtual NICs and virtualized memory. We forget about virtual CPU and virtual disk. All of these things are no longer a worry to us. Some people may still use them, but ultimately everything will be in the cloud as a service without any infrastructure that you need to worry about. And comparisons to APIs is also interesting. There is a big difference, but I'm not going to get into it now. Wow. I'm looking forward to going home tonight. How many of you got a flight tonight? Okay. How many of you are worried about your flight tonight? Well, I've got a flight in the morning back to San Francisco, so I probably won't be able to get that one. So, and the reason I kind of had that slide was because this slide, I pinched this from somebody else, kind of needs some context. It needs some additional context, otherwise it just doesn't make sense. And that is my proprietary vision of the cloud, of what serverless is. You can take it or leave it. And I'm happy to discuss it later on the Slack channel or in person. But ultimately, this brings business value for technical people, developers with a little d, as we call them nowadays. I run infrastructure and ops advocacy, and now people are not developers traditionally. But we struggle to come up with an appropriate technical term for everybody, including people in operations. So we tend to use developers, we are developer relations, and bandy that word around a lot, but it means technical people. So effectively, all of this gives value to developers and to people solving problems. Ultimately, this could be problems with data, problems with business logic, and such like. It also provides scale. And scale, in this case, when I first started talking about app engineers ago, I used to talk about how massively it can scale, but it's not important. The importance of scale is that it can scale to match your requirements and your needs and your imperatives, effectively. You can scale to 0, so it doesn't cost you anything when you have no work to do. These are all very, very powerful things. It's not so we can handle massive scale. It's about we can have the right amount of power at our disposal to be able to handle our workloads. The next thing is managed as well. Managed is also very, very interesting. Managed could imply that somebody's actually managing these things for you, but it's not. This is all automatic. These things are all done automatically for you. So you don't need to worry about it. Nobody else needs to have to worry about it either. And obviously, Amazon have to manage Lambda to a degree, but they have SREs on call to actually fix Lambda when it breaks. Interestingly enough, Google Cloud Functions had an outage today when Google Cloud Storage went down. But it was a very, very small outage. But our SREs manage that. You don't have to worry about any of it. And it's all managed behind the scenes automatically. And the next one is you pay only for what you use. And I'm not just talking about money here, because it's important to understand that serverless isn't just limited to the cloud. It's a very, very strong paradigm. Go back to the paradigm where we had provisioning of virtual machines and CPUs and memory and networking on demand in the cloud. That was a very, very powerful model. But we could also do it in our data centers where the cost wasn't the factor. It was the convenience of it. So now pay for what you use effectively means pay for the resources that you use, potentially. So if you're doing serverless in your own data centers, which you can do with things like OpenWhisk and in the future, Knative and others, then you will be using your own resources, but there will be no cost to your engineers, unless you're charging your engineers for your processing power, which is interesting. I don't think many of you do that. So basically, pay for what you use. That could be money, that could be resources. And so serverless is basically more than just functions. All of this stuff is ultimately going to be serverless. And there, your business logic here it doesn't work, does it? Your business logic here is functions, effectively. You having the ability to run code in the cloud. So functions as a service, a quick summary of them. This is basically what the bulk of the talk is about. It's not going to be talking about BigQuery. You can't monitor BigQuery, so it's probably not going to be much use having me talk to you about it. But talking about functions as a service in a very agnostic way, rather than talking about Lambda or anything, let's just think about the things that they offer. And we've covered some of these points already: managed automatically, code to business value, pay for only what you use, we've done, multiple invocations handled concurrently. Now that's massively important as well. Now the temptation is to think of instances. Hey, we'll have more instances. We'll have more, like we have more VMs. That you need to get away from that mindset. It's about being able to do multiple invocations concurrently, as many as you need, effectively. So think of this as taking your business logic and having it scale to run multiple invocations, rather than thinking of instances, because you can't SSH into those instances, as we're going to talk about on the next slide. The environments for serverless and functions as a service specifically come in different forms. Some are proprietary. App Engine, when it first started out, was proprietary. Not that proprietary, but proprietary enough that you would struggle to take your code and run it somewhere else, unless it was very, very simple. We had lots of very good convenience native APIs that were great, but you could only run them from within App Engine. So you couldn't take your code down and run it somewhere else. Nowadays that's changed with App Engine. With the new runtimes that we have, we can now run that code anywhere, but you may still be dependent on Google services. And then there's an open environment where your code runs anywhere. Runs anywhere, you may have to bootstrap the code because it's a function, basically. It doesn't have the framework around it to run it, so you may have to bootstrap that code to make it run. But it's fairly straightforward to get it up and running. We're going to cover requests and events very shortly. So some of my slides I put up as kind of straw men, so I can have an argument with myself about them, which is kind of interesting. It's always fun. Who ensures reliability? This slide came from a talk at Google Cloud Next recently. I tend to think of it differently, and I think Charity Majors kind of put me onto this a while back, and that's that reliability must be a shared goal, was what it said originally. That's not the case, right? Your cloud provider doesn't share your goals, ultimately, right? Your goals are your own. And their goals may align with yours frequently, but they won't always. Sometimes their goals will say, I'm going to have to sacrifice you so I can feed these people up here. So you have to understand that it's not always going to work for you the way you expect it to because of that shared responsibility. So don't assume that the cloud provider has your back all of the time. That may lead to ultimately things like multi-cloud, whereby you have to use another cloud provider to back up what you're doing in one cloud. That's definitely going to become a pattern of the future. And that's fine. Azure had a big outage, and it's horrible for them. The poor folks working on it, it's terrible. They had an outage, they're probably still going on, I'm not sure. But in those situations, you want to be able to fail over to a different cloud. Okay, so reliability is a shared responsibility across the cloud provider and you, but it's not necessarily a shared goal. Going back to this, we mentioned this earlier, forget about instances. Forget about things you can SSH in and check the logs on and such like and find out what they did wrong. These things are very, very ephemeral, just like pods in Kubernetes can be. Ultimately, get away from thinking you can SSH and look at the logs from within inside the instance and see what went wrong. That gives us a problem when it comes to monitoring, which we'll talk about shortly. Microservices, obviously you know about microservices, I know. So this slide is just to indicate that complexity increases as we decompose monolithic applications. Monoliths were fairly complicated, and their tight dependencies and tight coupling could cause significant cascade failures. But microservice decomposition requires that we find services, that we wire them together, and that has its own individual problems, and scaling them all separately. So tracking things through a bunch of microservices can be a problem. And then some event happens and it triggers a bunch of microservices, but something goes wrong. Somehow you need to be able to monitor that. And I think Jan covered a lot of that stuff yesterday, so I'm going to go in a little bit of a different direction. This is another straw man. This is talking about instances. So forget about instances. Don't worry about instances. Think about your business logic as a unit. You could have multiple units. You could have one unit servicing multiple requests. sequentially, effectively. So cold starts would become bootstrapping your business logic, effectively. So rather than thinking about this as a start in an instance, you think about it, what does it take to bootstrap your business logic? And can you do any of that in the background or lazily? So don't think about cold starts. That's the metaphor that we have currently, but it's much more about bootstrapping your business logic. And with functions, no code is executed outside of the request event handling. Not going to speak to that. And obviously, this is kind of difficult as well, and it goes back to tracing microservices. Asynchronous execution and events is very, very difficult to trace. And serverless is based on this, or at least functions of the service is based on this. Events, distributed task queues, message queues, fan out, fan in, all of these things are hard to trace. So I'm going to go into my little sample application. My little sample application takes an image, and it ultimately translates it into multiple different languages, or translates the text on it into multiple different languages. It's effectively an OCR. Okay? So it's made up of a bunch of functions, and I've used the agnostic function symbol to designate a function. The green things are message queues, topics, that kind of thing. Fairly easy to get your head around. It's not a particularly effective app, but what happens is we copy an image into the image store. That triggers some kind of event that fires off a function that pushes some jobs into a queue. I showed a fan out only for the actual function itself and not actually fan out into the queue. So in this case, we're going to get 5 jobs, 5 different languages we're going to translate that text into. Then we're going to push the results of that translation out into another queue, and that's ultimately going to go to another service that's actually a function that's going to store the translated text somewhere, into a database or into some storage. And it's important to mention that per language invocation there, so that's what the fan out is, and that one's a per result invocation. So there's multiple invocations of that bit of business logic. So the success scenario here is fairly straightforward. But the good thing about doing all of this with functions is that we can wire disparate systems together using the functions. Ultimately, we have an image going in one end, and we have coming out of the other end of the sausage factory is a bunch of translated text, which we can do some interesting things with, which we'll talk about shortly. But what happens if this happens? Nothing comes out of the function. The function fails for some reason. How do we handle that? How do we handle errors so that no data is lost ultimately? Well, the main way we're going to do that is through retries. And so we're going to retry things that fail. And this is really interesting as well. It plays into something that very, very fundamental at Google. And I'm talking about Google again, I apologize. But I think this is really, really important, that we assume that everything will fail. Everything is likely to fail, right? And so therefore, we build services such that a failure will not take the service down. Most of our failures and our outages are caused by updates that we do. We roll out an update, and it could take down a service. Because our cloud platform is also fairly emergent, or our infrastructure is fairly emergent, we can't always predict what a production rollout will do. And so that's one of the main reasons we have failures. It's not because a machine goes down. We will never have an outage because that machine over there went down, or that rack lost power. Right? Because we can handle all of that. So if you assume everything's going to fail and be prepared to retry, then you're going to be in a good place. All right? So retrying function executions is the simplest way to handle failures with serverless functions. Variants of serverless functions, we have a couple that we mentioned here. There are others as well, scheduling and such like. But a HTTP function would actually respond to HTTP requests. It will be synchronous, generally. And the retry here would be on the onus of the caller. The caller would have to detect that they got a 400 back or a 500 back and then make the retry. So this is going to be called at most once. We're going to call it once. It is either going to actually be a call or it's not going to be a call. With background functions, these are invoked by other services, things or message queues, or object notifications, or a row being entered into a database. These things will generate events, which are the background, ultimately going to drive background functions. These will be called at least once, and they may be called multiple times if a retry happens, because a retry is actually made by the provider in this case, by the FAS system. So these retries will happen automatically. So we had to handle that case as well. So let's look at that. More complicated case, not that complicated. Now we're going to do the translation, but we're also going to do sentiment analysis on it as well. So we use a function called NLP text that does natural language processing and looks at the sentiment. And what happens if one of them goes down? So the translate text function failed. And now we've written results, but maybe not the results that we want. This is a very trivial case, but imagine a financial transaction. We could retry translate text, and it would automatically. The function as a service system would retry this automatically, and we could end up in a very strange state because we may have modified something twice, and we didn't cater for that happening. So we have to worry about idempotency. How many of you know idempotency? All of you, right? Yeah, okay. It's a great word, right? When I learned that like 10 years ago, I was like, oh, okay, I didn't understand it before. So a function is considered idempotent if you can call it multiple times and the system will be in the same state regardless of how many times you call it. Now, this doesn't kind of cater for things like race conditions and such like. There are ways that idempotency can be kind of got around with retries, but ultimately what your goal is to make the function as idempotent as possible, so that whenever you do have a retry happen, if the original function call happened and was successful, the next one, the retry, wouldn't break it. You can use things like idempotency keys, and apologies, I'm using the Google Cloud logos here, but I couldn't think what to put there instead. So this is Google Cloud Functions, and that's Google Pub Sub. We have events coming from our message queue into a function. And some of these may fail, like 67890 probably failed 2 times and was retried twice. 54321 was retried once. So effectively, we can use this as an idempotency key because this value is always the same every time we retry it. Okay? So the system preserves that, what we call an event ID in Cloud Functions. But we use it as an idempotency key. And what we can do is, this is just an example, but you can act on that. You can do things based on that. You may record every single transaction, have some kind of journal system, so that you can roll things back if needed. You can understand what each thing changed. In this case, it's a very, very simple thing that we would use the event ID as a key, as a primary key in whatever data storage system we're using. So when we went to do it again, we would overwrite it exactly with the same data that we got in the first call. So that's one way of actually approaching idempotency. So that's very, very powerful. And again, race conditions notwithstanding, that would probably solve most of your problems. So now I'm going to go into an expanded version of our little app. Our app translated text. And what we're going to do is take save text here and replace it with a different one. And, what happened there? Okay. Come on. So now we're going to replace that previous endpoint for that app with text to image. It's going to get the images from the image stores, and it's going to then take the text and it's going to add a subtitle to the image. So we have the original text in the image, then we have the translated text added to it, overlaid on top of it. Okay? And so once that's done, we push that out to a queue, and then we can save the results back to somewhere. Okay, so this is interesting. We have some more things going on here, things like image magic that we're going to have to call. Our function code, and I hope you can read it. No, you can. It's quite big, isn't it? That's good. So our function code is fairly straightforward here. This is a function. This is Google Cloud Functions code. We have text to image as our function. The things highlighted in orange are the things I care about. We're going to create a temporary directory. We're going to download the image. We're going to draw some text on it, which is the caption. We're going to do an async write to that temporary directory. And then we're going to use some helper method to publish the result to the next part of the pipeline. Okay, so you can see any bugs with that code? All right, okay, so we need observability tools, and things like logging, alerting, monitoring, error reporting, and tracing are all going to help here. Tracing, not so much. So tracing is going to be my next talk, because in Cloud Functions, we're still not able to trace the way we would like. We trace everything at Google, but having a whole trace that shows us all of the invocations of a function is still beyond us currently, but we're getting close to that. So my next talk will be on how we can trace all these things and have really deep understanding of what's going on. So let's deploy and test this application. We do. We test it 5 QPS for about 5 minutes. We get some 503s coming. About 5% of them are failing. Not very good, right? And we look in Google Cloud Monitoring, and we can see that memory usage is about 256 megabytes. And that's the amount we allocated to this particular function. Okay, so we may be running out of memory here. We can dig into the logs, of course, and this is a Google Cloud login. So we just go into Cloud Functions, click on the View Logs button, and we can see all of the logs for that function. We have execution IDs, which we'll talk about as well. Event IDs, which we'll talk about as well. But basically, we can see everything that happened. And we can see memory limit exceeded. So we add some memory. We increase the size of our function. And normally, when you increase a function on Lambda or on Google Cloud Functions, it's like add more memory, add more CPU. Right? So you get some additional benefits from it. So we add more memory, and the 503s went down to about 2%, but the memory usage went up. And you can see that pattern of where we ramp up and then kind of top out, then you can see that's a real problem. You may understand what the problem is already. And it turns out, if we look at the original code, what was missing from that is that we didn't remove the file. Now, in Google Cloud Functions, that will count against the memory usage. I'm not sure about whether it does on Lambda, so I've not tested this on Lambda yet, but it could do. But ultimately, we add this line back, then we're going to clear out the temporary stuff as we exit the function. Okay, so that's very, very important. So instances of these functions stick around for a while, and they will leak memory if you're doing stuff like this. So we fix the memory leak by adding that line. Memory usage goes down. Okay, that's good. Should we reduce memory at this point? No, not necessarily. We could do. It might save us money. Depends what's important to you, money or time. So ultimately, we don't. We leave that alone, and then we can actually look at the whole analysis. And again, we don't have the tracing currently to be able to look at all the things that happen, one after the other. But we can actually see which events were triggered and how long they took in the logs. So in this case, we can see that creating a temp directory took 10 milliseconds, downloading the background took 80 milliseconds, writing results was 500 milliseconds, and uploading was 1,300 milliseconds. So we can also use custom metrics within Google Stackdriver or whatever monitoring tool you're using to be able to get more insight into what's going on. So in this case, we switched to better compression. We switched to PNG rather than writing to a bitmap. So that went down, and that helped reduce the time down to 0.9 seconds. And then finally, we optimized downloading the background image, the image that we had before, and we did that. Yeah, so like if you've already got the image cached, because we're going to be using this image 5 times. So currently what we would do is go and get the image 5 times, append the new text to it, and then write that off to wherever we need to go. But what we can do here is actually cache the image. We can't guarantee it's going to be cached, and it's going to be there available to us because we make it a different instance, but for the most part, it's going to be there. And we can also cold start bootstrapping our business logic by moving computations to the global scope. So in this case, we are creating a temporary local dir. That took some time. And getting the GCS bucket, Google Cloud Storage bucket, we moved that into a global scope. And now that happens on a per instance basis. And so we have multiple invocations of that instance, then we're going to save time because we didn't have to initialize all of that. So I'm going to quick plug for Google because I work for Google. So if you haven't used all of our products before, we have a very complete set of tools for monitoring, login, alerting, tracing. Google Cloud Trace is something I really do love. So that's going to be my next talk. Hopefully I'll get invited back to Monitorama at some point and give that talk as well. And that's pretty much it. So thank you and Q&A. Time for questions or?
Any questions? No? Going once? Going twice?
You can get me on the Slack channel. I'll be in the Slack channel. So I've got to fly home later this afternoon, but I will be looking at the Slack channel. And I'll stay on it for a while. How long do you keep the Slack channels up?
Indefinitely.
Indefinitely, okay.
Yeah, we just keep adding people to it.
Okay. Cool.
Yeah, Slack's going to be in touch with me sooner or later.
All right.
Yeah. All right. Thank you very much, Mandy.
Thank you. If you want to speak to me one-to-one, just ping me on the Slack channel.